All right, this is going to be one sample or single sample z-test. Really, we've been doing these all along because this has been the test that we have been using as the example as we go through hypothesis testing. A single sample test is done when we have a single sample that we want to compare to a known population. This would be the situations like we've been discussing. We know something about an IQ test, and we want to see if a sample of students scores better than average, worse than average, or is just different from average. This is a chart about the two different kinds of single sample tests from chapter 10 and when to use them. Excuse me. Forget what we know about n, what the textbook says about n, and we're just going to base our decision upon whether the sigma, the population standard deviation of the reference population, is known. If it is known, then we're going to do a z-test. If it is not known, then we are going to do a t-test. This show, we'll just really talk about t-tests, and next we'll get to the z-test. I'm sorry, the t-test. But forget anything in Top Hat. I went through and deleted most of it. But if it says anything, and this chart is in there, ignore what it says about the size of n factoring into the decision. And you see where I've crossed out some text and hidden some other boxes. All we're going to worry about is whether or not sigma for the reference population is known or not. If it is, it's a z. There we go. We'll get back to the other chart in a little bit. The t-test can be used if and only if the population standard deviation sigma is known. And I said earlier, ignore n. We need to know sigma because if we know sigma, let me grab my pen. If we know sigma, right, we can use the central limit theorem to find the standard error. In fact, you need sigma to find the standard error because the standard error is sigma over the square root of n. Pretend it's a lowercase n. So you need sigma in order to do a z-test. Here's the formula for the z-test that we've been using. And for any sample size, this is what we're going to do. This is what we've been using. Sample mean minus mu sub x bar. Right, that's missing there. That's a sub x bar there too. Right, from the central limit theorem is where we get these two things, and then it's just spelled out here. They got an extra symbol down there. So there's the formula for the z. It is a custom. Let me get rid of my stuff. It is what we have been using all along. That should look very familiar. So essentially a z-test is all we're doing is we're finding the z-score that corresponds to the sample mean. The critical values for a t-test, because it is a single curve in a normal distribution, the areas associated, the z-scores associated with the areas are fixed. It's a single curve. So if alpha is 0.05, here are the critical values for a single tailed test, a directional test. And remember, this is less than or greater than, and non-directional is it does not equal. So those will be the critical values. These are things you're definitely going to want to make sure you have on a cheat sheet, and there's even, I'll show you where you can find them elsewhere. At this point, take a break and look at the Stats Garage clip on single sample z-score. I wasn't able to insert the entire clip into this PowerPoint presentation, so I just thought I would take it, just refer you to that outside of it. So take a break, look at that clip, and then come back. All right, so you see from that clip, it really just is what we have been doing all along. You should be pretty good at this by this point. So what do we have? Really going to be working these from word problems. And if the problem wording contains one of those kinds of phrases, now don't be too specific, right? Less than, there it's in quotes. Anything that says worse, not as good as, below, right, means less than. So then there's the sign we would use for the alternative. And that's actually wrong. These are slides from Top Hat. There was no equal sign in the alternative, just a straight up less than and a straight up greater than. Right? So less than here, less than is called a left-tailed test. Greater than is a right-tailed test, and then there's the two-tailed. This shows the rejection region for a one-tailed test, really a right-tailed test. This is for an alternative hypothesis that has a greater than. It is also level of significance here is alpha is 0.05, and this is rejection region, but it got cut off when I cropped the picture. There's the critical value of z. Because a normal curve is a single curve, whenever it's 0.05 and a greater than in the alternative, the critical value is 1.645. Really, we've been using 1.65, just round it to 2 decimals. For a left-tailed test, which would be when the alternative is a less than, and here again, alpha is 0.05, the critical value is negative 1.645. So this would be the rejection region right over here. Two-tailed tests are a bit more complicated, and this shows the two-tailed test rejection region. Right, if alpha is 0.05, we're using the z-test for this, so the critical values are positive 1.96, negative 1.96. We would reject the null hypothesis if the outcome is in either tail. It can't be in both. We only have one outcome. But, right, this is important. Where it is, which tail it is in, tells you whether we have above average, greater than, or below average. When we're doing a two-tailed test, we don't know ahead of time. We don't have any sense of direction. We just want to see if people are different from the population. Think of an IQ test. Someone wants to know if their students are different in terms of IQ. Difference is a vague word. Difference means they could be below average. Difference means they could be above average. Going in, we don't know. But coming out, when we get a result, we're going to know whether that sample is above average or below average by where the outcome is. Anytime we get a z-score that is in the rejection region in the right tail, that tells us that people are above average. Whenever we get an outcome that is in the lower tail rejection region, we know then that the sample is below average. The rest of the show is going to cover one sample t-test, and I think I'll be able to get through it. I'm sorry for the coughing. My allergies are killing me. I don't think I have the plague. I think it's just allergies. At least that's what I'm hoping. The one sample t-test is used really when we cannot use a z-test. And that situation is when we do not know what sigma is. Let me go back. Right? If we don't know what sigma is, if we don't know the population standard deviation, you can't do a z-test because you cannot find the standard error. This is where the t-test comes in. The story behind the t-test is the story of William Gossett, who worked for Guinness Brewing Company. And Guinness, back in the day when they were industrializing and starting to produce massive amounts of beer, recognized that quality control was important. So Gossett worked for Guinness, and he knew the targets. Effectively, he knew the mu that they wanted their beer to have in terms of different properties. Properties of beer include alcohol content, specific gravity, which is how much stuff is floating in it, There's scales for rating the color. There's scales for rating the frothiness. There's a variety of measures one can take. And Guinness defined what they wanted in terms of means on these target means on these different parameters. And these effectively were population means mu. But they had no idea what the variability was on these things. So Gossett, being a mathematician, put himself to work and realized that if you don't have sigma, you could substitute in the sample standard deviation S in its place. And you could estimate the standard error, we call that S sub x bar, the estimate of the standard error, by simply substituting in S for the square root, for S for sigma. So Gossett realized by doing this substitution, he could do a hypothesis test to determine whether a particular batch of beer was significantly different, right, above or below their target value for mu. Now, Gossett, in doing this, worked out all the math. We don't have to do it. We just have to trust him. So a t-test is at one level a substitution. We use S, the sample standard deviation, instead of the population standard deviation to do the hypothesis test. We still can use the central limit theorem, but we just have to fudge it a little bit with information from the sample. The other thing Gossett realized is that when you're using this thing that he called T, you're not using a normal curve anymore. You're using a distribution that's a little bit different from the normal curve. And really, he found that the t distribution is determined by the degrees of freedom, which is in turn, it says there, determined by the sample size n. Effectively, there is a different t distribution for every possible degree of freedom, with infinitely many degrees of freedom, right? df, we're going to call degrees of freedom df, right? With infinitely many degrees of freedom. Right, there's the infinity symbol, right? The t distribution equals the z distribution. They're the same. But in reality, we never have infinitely many degrees of freedom because we have n minus 1 for our degrees of freedom. So any kind of degrees of freedom less than infinity, the t distribution is not the same as the z. So how does it change things? Well, what happens is that as degrees of freedom decrease, what happens is that the t distributions get shorter in the top and a little fatter in the bottoms. They get smushed. It gets shorter in the top and wider, fatter in the tails. So the red curve, say, is a standard normal curve. Dark blue is degrees of freedom of 5. Light blue is degrees of freedom of 2. Right? See, df2 is a little shorter. But look what that does out here, right? If this is 5% of the red line, to get 5% of the df equals 2, we've got to move the critical value further out, maybe somewhere like here, right, to get 5% of the blue, because it's wider. There's more turf out here in a t distribution than in a normal curve. So what does that do? It changes the critical values of t. Essentially, for our t-test, there is a different critical value for every degree of freedom, because degrees of freedom equal n minus 1, right? So effectively, for every different n, there's a different critical value that we use in the rejection region. Now remember degrees of freedom. Way back when we were figuring standard deviations, I did the demonstration with the 3 chairs in the front. And how when we have 3 chairs and 3 people making choices of where to sit, right, we only have 2 degrees of freedom. Same thing happens with numbers. When we use the mean to find a standard deviation, we know something about the distribution and we lose a degree of freedom. All we need to worry about here, right? Go back and review that. But all we really need to worry about here is that for a t-test, df, degrees of freedom, equals n minus 1. Here's the formula for a t-test, and it should look familiar. It is essentially the same as for the z, but I don't like that there. This is kind of prepackaged from Top Hat. I really think this should be s sub x bar because we're estimating the standard error. So to compute a one sample t-test, we still need to know the mean for the population, right? And then we use the central limit theorem to find mu sub x bar. But we use the standard deviation of the sample to come up with the denominator. So for the reference population, if we know mu, but sigma is unknown, right, we still can do work because we have an S, we have sample data. We have a sample standard deviation and a sample mean. So we can still do the test. All right. So what matters, right? In order to look up the critical value of a t, because earlier, remember we said, right, now we need to know there's a different curve, a different distribution for each n. We need to know alpha level, which is 0.05 or 0.01. We need to know whether it's one-tailed or two-tailed. Notice those are the same things as a z-test. But now we add in the degrees of freedom, right, which is n minus 1. Right, so whether the alternative hypothesis is one-tailed or two-tailed matters, alpha level matters, same as the z. This is what's new right here. This is not the exact table that is in Top Hat, but it is set up the same way. And I scanned it in so that we could look at it together. But this works the same way as the Top Hat table. Notice there's dual headings, right? Proportion in one tail or proportion in two tails, right? So this is where knowing the sign from the alternative comes in. If it is less than or greater than, you use these top row of column headings. If it does not equal, then we're going to use the bottom row of column headings. The other thing, remember, that matters is the level of significance. Well, here's 0.05. One tail. Here's 0.05, two-tailed. Here's 0.01, one-tailed, and it's hard to see, but it's over here. Here's 0.01, two-tailed. So the sign from the alternative and the alpha level of significance, get you to the right column, right? And they're able to save some space by using these dual headings. Over here, the rows are labeled degrees of freedom. Right? The rows capture each degree of freedom. So on this table, if we have degrees of freedom equal, let's say 10, right? 10 degrees of freedom, alpha 0.05, and we have, let's say a less than, right, in the alternative hypothesis. So one tail, 0.05, and then we read down to this entry right here, the critical value is 1.812, right? So in setting up the rejection region, right, 1.812, and it would be negative, is the t-value that marks off 5%, marks off the rejection region. Now think for a second, if this was a z-test, right, it would be negative 1.65 would be the critical value. Remember we said the t has more area in the tail, right? So for any given degrees of freedom, the critical value becomes larger. Right? This is why t-tests are seen as more conservative, right? You reject the null hypothesis only if the t-value we calculate is greater than this critical value. The fact that it's higher means it's harder to achieve. Okay, let's try. Oh, sorry about that. Let's try that table again. Let me erase everything here. Now let's do another one. Let's do alpha 0.01. Uh, Alternative has does not equal, and let's say that n equals 7. All right, now look what I did here, right? Alpha 0.01, two tailed. So here's two tailed. Here's alpha 0.01 down here in this shaded area. It didn't scan real well. And then we need to find the right row, right? So here's the column we want. Now n equals 7. We need the degrees of freedom. Degrees of freedom is n minus 1. So here degrees of freedom is 6. So reading across from 6, there we go. The critical value of t is 3.707. Now, as I said, this is when I scanned in, but it's formatted the same way as the one in Top Hat. Make sure you can find these two things using that table in Top Hat. And again, here's another example. Sorry, this one should have come first. Two-tailed 0.05, two-tailed 0.05 for 9 degrees of freedom is down here 2.262. Now that's two-tailed, right? So what would it be like? Well, think back to the earlier chart that showed the two-tailed test that looked a lot better than my sad drawing here, right? Negative 2.262 for that one. Positive 2.262 for that one. So we would reject the null hypothesis if the t we obtain is less than negative 2.262 or greater than positive 2.262. Now I did post an example of a t-test. Again, I couldn't embed it. It was too big a file to embed in the slideshow. But take a moment here, stop while all this is fresh, and review that Stats Garage example of a t-test. The final thing I want to do is reiterate these steps of hypothesis testing. The steps are the same whether it's a t-test or a z-test. And remember, the difference is whether or not we know the population standard deviation sigma. So for both tests, the first step is always state the hypotheses, right? Identify the null and the alternative. The null always has an equal sign. The alternative has a greater than, a less than, or a does not equal. Right, now this is where sometimes in Top Hat they'll show you, right, a less than or equal to, right, because that matches up technically better with less than. Greater than or equal to technically matches up better with a greater than. But I'm happy, I'm content, I like using this one. If you use this one, you will not be wrong in my class. But I want you to see technically why the Top Hat is kind of right. I'm going to give them a break on this one and say they're technically correct. The two hypotheses should be mutually exclusive and cover all possibilities. And technically, when you just use an equal sign, it doesn't do that. But we can look past that. I will look past that. And if you have an equal in the null, I'm happy. The rejection region, right? This chart summarizes the rejection region. Let me get this out of here. We'll just go away. There it goes. First, we got to determine the appropriate test to use. Is the population standard deviation known? Yes. It's a z-test? No, it's a t-test. Then to find the rejection region, the critical value for a z, we need the sign from the alternative. We need to know alpha. For a t-test, need the sign from the alternative, alpha, and also this thing, degrees of freedom, which for the t-test, single sample t-test, is n-1. The third step has always been to conduct the statistical test. There we go. Is to do the t-test. And I was able to get these two formulas next to each other so you can see them. T-test and z-test are really the same thing. The steps are the same. Earlier I made the change. I would say rather than that, I kind of like this written in there, right? Because we have to estimate. If we don't know sigma, we have to estimate it using the sample standard deviation, and that is an S. The estimate standard error is S sub x bar. But here's the formula. That becomes the denominator of the t. And again, here's the summary chart. This is a much better chart than the trash that's in the book. The fourth step is the decision and the conclusion. So the decision means comparing the calculated statistic, the z or t we obtain, which we get in step 3, compare that back to the critical value from step 2, and we decide to reject or fail to reject. No matter whether it's a t or a z, the logic is always the same. If it's in the rejection region, if it exceeds, right, more extreme than the critical value, then we reject HO. The conclusion is going back and interpreting this decision in terms of the original problem, right? We want to summarize what we have found. And this is really the most important step. This demonstrates that you understand hypothesis testing because you're able to take what we've done and apply it back to the problem, right? Think of this as being, if you're doing an honors thesis or a master's thesis and you say, well, my t-test is 12.92. You need to know what that tells you about your data, about the study. We're not doing this just to figure out what the t is. We're doing it in order to figure out whether the sample is different from the population in a way that is meaningful. So you want to go back and put that back into words. Fortunately, right, it's yoked. If you reject the null hypothesis, the conclusion always starts off. It's okay to start it off like this all the time. We have evidence for H1, but just don't say H1. Put H1 back into words. So you might say, we have evidence that these students are above average in intelligence. We have evidence that these students are below average in intelligence. If it's a two-tailed test, it's tempting to say we reject the null hypothesis. We have evidence that these students are different. That's correct, but incomplete. If you go to your child's parent-teacher conference and the teacher says, boy, your kid is different, right? You want to know how they're different. So if it's two-tailed, be sure that you say how they are different. We have evidence. Right? Reject the null hypothesis. We have evidence that these students are different. We have found that they are above average in intelligence. If you fail to reject, then we have no evidence, right? Just put that word no in right there. It's important. We have no evidence for the alternative. If we fail to reject the null hypothesis, we have no evidence that these students are below average. We have no evidence that these students are above average. Right? Where the no goes is always important. It goes in front of evidence. Because if you say, we have evidence these children are not different, that's really not the same. Then you're saying you have evidence in favor of the null, and it's never true. All right, be well, and I'll see you soon.